So good morning, everyone. I hope you are all doing great. Welcome to the seminar of this week. And today we are very delighted to have with us Dr. Palash Panja from University of Utah. The title of his talk is Machine Learning and Data Analytics for Geoscience Applications. Palash is a research scientist at Energy and Geoscience Institute and a research assistant professor in the Department of Chemical Engineering at the University of Utah. He worked 5 years in chemical, petrochemical, and E&P companies. His current research areas include data analysis, machine learning, flow in porous media, geothermal energy extraction and storage, flow assurance, and direct air capture. He has published more than 50 articles in journals and conferences. Thanks, Palash, for accepting our invitation, and the floor is yours.
Yeah, thank you, Tom, for a nice introduction. As you mentioned, I am a research assistant professor in the Department of Chemical Engineering and research scientist at Energy and Geoscience Institute, University of Utah. Currently, I am working on various research topics. These include geothermal, extraction of REE, rare earth elements, data analytics and machine learning, energy storage, carbon dioxide capture, utilization, and sequestration or storage. And of course, oil and gas is my main research areas. That was my part of my PhD during Shale revolution in 2010-2014 time period. Other than doing research in oil and gas, I tried to explore other avenues, like you can see renewable energy like geothermal, and without research in energy storage, we cannot get renewable energy moving forward, because we have some problem with the storage. We don't have commercial storage other than lithium-ion batteries for renewable energy storage. So we are working on energy storage also. But today's topic is not about other things, but machine learning and data analytics. So I will focus mostly on oil and gas and application of data analytics and machine learning in oil and gas field mostly.
Hi, Palash. I very much apologize for interrupting you. Do we happen to have your permission to record the talk?
Yes. Yes.
Yeah, actually, I've asked it, Lawrence. Sorry for it. Yeah, we've confirmed with Palash and got a yes.
Oh, you are already recording. Excellent. Thank you so much. I apologize.
Yeah. And Tom asked me in email also that the permission. Yeah. So mainly in today's seminar, I will discuss data analytics and machine learning in oil and gas application, and broadly geoscience. So you are very much familiar with this diagram. This is well-known diagram or workflow for subsurface characterization, starting from seismic interpretation. And I think energy, your laboratory, ERL, is very well known for seismic interpretation research. And that's the first part of any development in oil and gas or subsurface development. Then we use a log, a wireline log, and nowadays we are using a 4D seismic interpretation also. And I am not going to describe all these things. This is the workflow to develop a reservoir model. Then first geologic model, then we develop the reservoir flow model, and we run the simulation to predict, to visualize the pressure profile or saturation profile, And after shale revolution, we also introduced the fracture in the model. Initially in the conventional reservoir, we didn't have a fracture model. Now we are struggling to introduce mainly DFN, discrete fracture network modeling, for natural fracture and also hydraulic fracture. And so that makes it complicated to prepare a reservoir model. And in all these components, we can apply conventional method of seismic interpretation or log interpretation. There are many softwares, many companies, but we can also apply the machine learning also in data analytics to improve the efficiency, to avoid any human errors in interpretation. So we can apply machine learning in different components. On the right hand side, I have provided a list, like of course seismic interpretation at the first place. Then once we have exploratory oil or even the production oil also, we can collect the oil log data. We can during drilling, we can collect core data, cuttings. We can collect outcrops. So using those data, we can use machine learning to interpret various properties. And also we can apply machine learning for fluid modeling other than reservoir numerical simulation. We can apply top-down modeling and machine learning. One kind of machine learning, reinforcement learning, we can apply that for optimization, operational optimization, as well as completion optimization, like during drilling, during frac job. And other model we can develop for field development. Already we have some oils in the field. How you can improve the recovery factor by drilling more oil? Machine learning can tell us where to drill, where is the sweet spot. So in today's talk, I'm not going to discuss all these areas, but I will trim down to few topics. So currently, I'm working on these 4 projects related to only machine learning and data analytics. Main project I'm working on, sponsored by NETL DOE, and it's called SMART project. It is acronym SMART. It's not. I will in a little bit. I'll discuss in a bit. Then I'm working on developing one tool. It's called Shale Smart at the University of Utah at Energy and Geoscience Institute for our corporate associates, company partners. Then I'm also analyzing data from FORGE, the Frontier Observatory Research in Geothermal Energy. I think that's the full form of FORGE. We have the biggest FORGE project in Utah, and I'm also part of that. I'm analyzing some data to using machine learning to predict like a rate of penetration or compressive strain. We are using like drill bit vibration at the real time. Also, I'm working on other projects like how to predict algal bloom in our Utah Lake. We have 2 big lakes here, Great Salt Lake and Utah Lake. So Utah Lake, we have problem with algal bloom, and I'm working on a project to predict algal bloom. I am working on another project. It's ARPA-E, DOE ARPA-E sponsored. It's a carbon dioxide in soil, and acronym of this project is SOCNET, Soil Organic Carbon Network, something, network. So, but today I will focus mainly on these first 2 projects for machine learning part, SMART and Shale Smart developed at University of Utah. So in the SMART project, I will briefly give you the overview. Then I have developed 2 models. One is temporal modeling, rate to predict rates, and another is the spatio-temporal modeling to predict pressure and saturation in the subsurface. So this project is collaborated among many universities and national labs. You can see in this list, almost all major national laboratories are involved. and all major universities are involved in this project. And SMART, the full form is actually science-informed machine learning to accelerate real-time decision in a carbon storage application. So in this project, carbon storage, we are not doing carbon storage, we are doing carbon utilization for enhanced oil recovery for EOR. So yeah, I am here as part of the university. So objective of the SMART projects are three. First objective is real-time visualization. So one group is developing visualization tools to visualize the data, subsurface data, so that people can interact with this data. The second objective is rapid prediction of reservoir behavior, and also we can using that we can take management decision. And third objective is real-time forecasting also. It is mainly this real-time forecasting is my project, so it's a part of one task. So I am involved in real-time forecasting, and it's mainly for carbon dioxide storage. So this chart shows you the interconnection between among all these tasks and subtasks. So first task is like collect data. Different type of data are collected, mainly pressure, temperature, seismic, and microseismic, then distribution temperature sensing, ERT, and BG. Then this data is collected and curated. Then this data is sent to the next level for modeling, and there is different group for modeling. And mainly I am part of this task for optimizing the carbon dioxide storage in terms of EOR. And different group is doing like fracture modeling, stress modeling, porosity and permeability modeling. I am doing mainly rate prediction on the surface and pressure and saturation prediction in the subsurface. So for this purpose, I am using this SACROC model. This is very well-known formation in Texas. The full form is Curry Area Canyon Reef Operators Committee, but it is well known as SACROC oil field. This field is operated since like late 90s, 50s, and they started CO2 EOR since 1972. And in this model, we have 45 oils. Actually, it has many oils, hundreds of oils, but we have a coarse grid model where we have 23 producers and 23 injectors. And you can see in the middle picture, the injectors are spotted in a 5-spot injection scheme. So there are different injection scheme. You are in EOR method, enhanced oil recovery method. So this is the 5-spot scheme, where one production oil is the middle, and other 4 injection oils are surrounded. And in this injection oil, we are injecting carbon dioxide and water, and they are alternating annually. And oils are randomly shut in to mimic the field operation. And the results are generated using the commercial software. We ran the software simulator for 30 years. And on the right-hand side figure, bottom figure, you can see the rate is not like monotonically decreasing. It is decreasing overall, but it is decreasing sometimes, that it's increasing. This is due to the injection scheme, EOR scheme. And it is not proportionally increasing or decreasing, because we are injecting carbon dioxide sometimes, we are injecting water sometimes. And to predict this rate, it's not easy to predict this type of rate. If you are familiar with ARPS model, for conventional reservoirs. Earth's decline method is developed in 1945. It is well known, and it is used for monotonous declining rate. And there are many other methods developed later for shale oil prediction. And none of those methods is applied for this type of sinusoidal rate. So you need advanced method like machine learning to predict this type of method, this type of rate. There are quite a bit of methods developed for time series modeling. One of them, which is most popular, is LSTM, or long short-term memory. There are many other like transformer, TCN, I think time convolutional network or something like that. But LSTM is the most popular. And this figure on the top can be found in Google if you search LSTM. I have given the link below. And these are the 6 main equations solved in this LSTM model. So I have developed the LSTM network on the right-hand side, which is stacked LSTM model. So there are 2 LSTM layers, and on the top, there are 2 ANN layers to predict the rates. We have oil rates, we have gas rates, and we have water rates. Initially, we tried to find out what are the inputs in the LSTM model. We tried, okay, input may be the historical rate to predict the future rate. Then in the second model, we tried, okay, let's take a rate plus bottom hole pressure. And in the third model, we tried to take rate, bottom hole pressure of the production well, as well as bottom hole pressure of all surrounded injection well. And I will discuss mainly, finally, we found that we get more accurate results with the third model, and I will show you some results with the third model. And for this, the inputs are not straightforward in LSTM model. You have to choose different ways to program this LSTM model. So during training, we had 8 features, 3 rates at all time steps, historical time step, and 1 producer bottom hole pressure and 4 injectors bottom hole pressure. But during testing, because we don't, it's a blind testing, we don't have old rates. We cannot use old rates. We have only the models. And operator will ask you, okay, if I know the BHP bottom hole pressure of producer, if I know the bottom hole pressure for injector, tell me the rate from this producer. And you have the model. That's why it has 5 features. Okay. And output would be rates, all type of rates, oil rates, water rates, and gas rates. And I have also provided the metric for during training. You can see that during training, we have I means injection bottom hole pressure, and R means rate. So I1, 2, 3 means the previous rate, and R-4 is the next time step rate. And in the testing set, you can see we first start with the historical rate, but in the second row, if you go to the testing metric input in the second row, that we are using the R dash T1 T+1 in the input. So whatever we are predicting in the first time step, we are taking that output into the input in the next time step. And that way we are, it is like a moving input. So these are the structure of input and output for training and testing. Let me show you the results. So we have 23 producer, but I have shown you like only results from 5 producer, P2, P7, P15, P20, and P22. The first row is the oil rate, second row is the gas rate, and third row is the water rate. You can see that in the P2, the first picture on the left top, the predicted rate marked as a blue color is perfectly matched, almost perfectly matched with the actual data, the green dots. And some cases it did not match, like last P22. You can see there is aberration between the actual rate and test rate. Of course, during training, in all cases, we have good results, but during testing, we had some aberration. We had good results with some oils, P2, like P7, but we had bad results with like last few oils, like P20, P22. And the oil rate always decreases because, you know, the amount of oil is finite inside the reservoir, but the gas rate and water rate are increasing because we are injecting water and gas. So over the time, we are getting higher water. And if I zoom in some oil to show you more details, and I have compared my result with ARIMA method also. ARIMA is a very common statistical method for regression. And you can see the ARIMA method fails to predict in the test time. It is good during the testing, during training, but it is bad during blind testing. But in our LSTM model, the blue lines, it can follow the trend at least. And this is only the test side to show you how ARIMA method fails to predict. And our method, the LSTM method, is almost perfect for at least for oil P2. And these are the performance analysis using a MAP, mean absolute percentage error, and NAC, and normalized NNAC. You can see that MAP is during training, MAP is around below 15%, except for few oils, it went very high, like P8, it went 435%. And for gas rate, it went 34%, and for water rate, it went above 25%. But NNAC is almost 1 during the training. And testing, of course, it's not very good. MAP was less than 50% for oil rate, less than 50% for gas rate also, and less than 30% for water rate. And NNAC is less than 1. On an average, it's like 0.5. So another model we have developed for saturation and pressure prediction. And for that, we have used convolutional long short-term memory. It's called convolutional LSTM. And on the right-hand side, you can see the structure of the network we have programmed. It has 2 convolutional LSTM on the bottom and 2 3D convolutional layer on the top. For result comparison, we compared them side by side, predicted frame versus actual frame, and we have measured structural similarity index and normalized root mean square error. And this is our workflow because we are using the simulated data. To get the spatiotemporal data, we have written an in-house code. It's called a DGrid. It is available in the NETL data repository. It's EDX. And using that, we have collected the spatiotemporal data. And then we pre-process data like data normalization. Then we have separated the result data for the layer of the perforation. In this model, we have perforation on the 4 layers only, not all layers. And in some cases, in the machine learning, it's difficult to handle this type of. On the right hand side, you can see the blank white space on the top figure. That means reservoir doesn't exist on that part, but machine learning doesn't know that. So we have to fill those gaps to make it like one rectangular grid. So we have, before the machine learning application, we have to do all this pre-processing. So this is the inputs. These are the inputs and outputs for convolutional network. During training, we have historical maps of pressure, carbon dioxide saturation, oil saturation, and water saturation. And during testing, we use the last few maps from the training set and we proceed. And output is pressure and saturation. This rate is, I think, typos. It should be pressure and saturation map. And in this convolutional LSTM, you need to predict. You need to give historical maps to predict the future maps, but it has inherent limitation. Convolutional LSTM will give you output same size as input. So in this example, you can see if the input is 3 frames, the output will be 3 frames. And there are 2 ways it can predict. It can give you the 3 future. Like if you give T1, T2, T3, it can give you T4, T5, T6. And another method is it can give you T2, T3, T4. 2 frames are overlapped, T2 and T3. So I have used this overlapping method because I got better results using this. And you take this final last one, T4, as your output. And yeah, these are some videos in the left side. It's mainly the difference between the predicted frame and actual frame. And in the right hand side, we have same for testing. Left hand side, same training. We have sometimes we have a lot of errors. You can see sometimes the red like 0.15 pops up. And during training, we had less errors, and during testing, we had major error on some spots, not all grids, but some grids had more errors. You can see for like red or brown pixels, they have almost 0.75 error. Because this is really a complex reservoir, it is heterogeneous in porosity, heterogeneous in permeability, and that the EOR operation is also complex because we are injecting water and carbon dioxide. This is basically a snapshot from this previous slide, the videos. Like first row is the prediction in the training period, and then the second row is the prediction the last stage of the training period. Similarly, third row is the first prediction during testing, and last row is the last prediction during testing. And on the right hand side, SSIM, like structural similarity index metric, you can see during training it is almost 1. That means it's good, but during testing it drops quickly below like 0.6. It's around drops to 0.4. And normalized root mean square error is also during testing. During training it's below 6%, but during testing it goes up to like 10-11%. Yeah, we have some other results for carbon dioxide saturation. That was for oil production. That was for pressure saturation, pressure map. This is for carbon dioxide saturation. Yeah, and we observed the similar results actually. During training, it was good. SSIM was close to 1, but during testing, it drops quickly because we are predicting the multi-stage ahead prediction. So we are predicting like 60 months or 5 years of saturation. That's why these results can be accepted for like 1 year or 2 years, but when you predict 5 years, it fails. So here is the summary from my first part of the talk, the temporal LSTM. So main key factors is the identifying the factors which influence the output. It is not sometimes easy for complex system, complex reservoir or complex subsurface system, but you have to try a different combination to get the right factors. I think LSTM is very promising time series prediction compared to other conventional method to predict the complex rates or complex time series data. It can capture the unusual trend like sinusoidal type of rate very efficiently. For spatio-temporal method, it is good, but problem is that if you want to predict like 5 years, 10 years, it is not that good. If you want to predict like 1 year or 2 years, the results can be accepted. So let me quickly, how much time do I have? Yeah, I have 15 minutes. This is the next project I will discuss with you. This is the Shale Smart project sponsored in-house, University Utah. We are developing. I will give you some overview, then I will show you some example and results. So basically, we are developing one tool using mainly Python code and other graphical user interface. So we are trying to develop the tool that will be used for prediction, interpretation, and data analysis in geoscience areas. And we are trying to develop also top-down type model. So if we have the production data or oil log data, how do you predict the saturation, pressure map inside reservoir? And we are also trying to do some research on remote sensing data to capture like methane emission or other type of leakage. So what are the data sources for this project? Of course, we have SCM image, scanning electron microscope image, and other images. We have core data, we have cuttings and outcrops, and we have collected production data that are available publicly. I will discuss a little bit more on that. We have oil line logs. We have laboratory test data using pyrolysis like TOC, hydrocarbon content, PVT, some seismic data, oil test data, and remote sensing images. So what are the challenges in oil and gas industry for data, collecting data? So you know that there are huge amount of data are stored in companies' repository, but they are not available for research. Sometimes if you have project with companies, with single companies, then they can provide you some information, but if it is a group project, then we cannot get this type of data. So you see that almost no geological data is available public, like no permeability, no porosity, no compressibility. So we do not have any geological data about any reservoir. Operational data, we have some data like production rate, peak month date, or gas oil ratio, but we have no idea about the bottom hole pressure, and that is very important factor actually. Completion data, we don't have any idea about how much propellant they have injected during fracture job. We don't have any data about fracture spacing, but we have some data about like location or perforated interval. That means basically the horizontal length. Finally, we do not know about fluid properties like PVT, formation volume factor, gas oil ratio. So with these constants, we have collected some data which are publicly available, and we applied our data analytics tools to get some insight. So we could do better if we would have all entire data set. But we are trying to do like one example. Actually, we have 3 examples here. We are trying to do machine learning in different scales. In the first picture, you can see the pore scale application. If you have SCM image, you can do segmentation using machine learning to find out where is kerosene, where is pore or cracks, where is matrix without porosity, where is some minerals. And this is a pore scale application. Then we can go to next level like oil bore application or oil scale. If you have resistivity image, we can identify different lithophases. And then we can extend our machine learning application to basin scale. Like if you have oil line logs, different type of log, resistivity log, gamma logs, we can identify a layer of interest, not only hydrocarbon layer. Sometimes this method is applied for identifying gold layer or other mineral layers. So we are working on this type of application. Our final tools are not ready yet. This is a top-down model. You know, if you have oil line data, and then you can interpret like porosity or permeability near wellbore region, and then you can apply kriging, traditional kriging or deep kriging using machine learning to get the permeability or porosity for entire reservoir. So you can get the spatial distribution. Then applying the Voronoi diagram, you can assign regions for individual wells, and you can overlap these 2 things to get the properties for individual wells, and then you can average them down to assign the single value of porosity or permeability for each region. This is mainly useful for many type of things, like you can do different reservoir engineering calculation to get original oil in place, OIP, recovery factor, estimated ultimate recovery, and finally you can do field development. Suppose you have the right-hand side figure and you know how much you have recovered already and how much are left, and you are planning for drilling few other wells in this area. So you can apply this type of analysis to get an estimation that how much you will get if you have new wells. And we have almost completed this type of study. Let's last few minutes, I will discuss the data analytics, purely data analytics. And you know that this right-hand side picture is really popular in oil and gas industry. This is for lower 48 state shale plays, and there are few prolific plays like Basin, Eagle Ford, Austin Chalk, Niobrara, and right now Permian Basin in Texas and New Mexico. Because I already discussed, we don't have a lot of geologic data and other data, so we have collected the production data, location, true vertical depth, lateral length, this type of data, almost from all the prolific shale plays or tight formation. We have around 80,000 wells data. Using this data, we did different type of plots, about 25 different type of plots. We have published few articles on this, and few articles are under review, so I cannot disclose all this data. Like reservoir depth, in the left-hand side figure, it's basically longitude, latitude, and colored by true vertical depth. It is the Eagle Ford map. You can see that reservoir is dipping toward the southeast, that light color. It's dipping towards like 14,000 feet. And the left-hand side or northwest side is like 4,000 to 6,000. So we can easily visualize that that structure of the reservoir. Then if you plot the true vertical depth versus like normalized production means we have cumulative data like after 10 years of production. We have the length of the horizontal oil because we are dealing with thousands of oils. They have different lateral length, different horizontal sections, and they have produced for different months. Some oils are being exploited for like 10 years, some are like 5 years. So we have normalized with lateral length and production time. Then we plotted them to find out where is the sweet spot. And in this figure, you can see in the Eagle Ford, around like 12,000 to 10,000 feet, we have the sweet spot, or we have that most of the oils are drilled. So for the future development, mostly operators or E&P companies will drill nearby that point, or that depth between the 10,000 to 12,000 depth. Also, we studied the impact of lateral length. If you plot in the x-axis lateral length versus normalized production in the y-axis, you can see this is declining actually. It is not always, if you add the lateral more, if you drill more longer horizontal oil, it does not mean you will get more incremental production. You will get little bit more production, but it's not like incrementally you are increasing the production. And we are also trying to find out what are the technological impacts on production. So we plotted with when the oils are drilled, like we have plotted around like 2006 to 2000 around 20s oil, and they are drilled. And you can see that it is increased actually overall production, the boundary is increasing. This is mainly because of the efficiency of the fracturing job. So day by day, the fracturing job is improved technologically, better sand, better fluid of injection. So from purely data analytics, with some constant, we can find out some insightful information. We have done other data analytics, like how the production is declining. And you will be surprised to see that production is declined to like 80 to 70%, 70 to 80% the first year. This is mainly shale, not the conventional reservoir. In the first column, bottom figure, you can see the first year production is like 90 to 29%. That means it's dropped to 70 to 80% from the first year, first production. And the end of the second year, it's almost gone. So like 90% to, it's dropped to 90% to 80%. And some operators are doing better than others, like EOG. This company is doing great in Eagle Ford. And in Niobrara, Nobel, they are doing great. And also we have calculated recovery factor, and the rightmost column, you can see the recovery factors, assuming some porosity, some thickness, because we don't have those values. And you can see average porosity, average recovery factor is like 3-4% only from shale. Of course, some oils have around 20% recovery factor, but on an average, it is like 3-4%. And this is very frustrating for shale development. We are drilling like millions of dollar oil, and we are getting like 5%, 7% recovery. So we are doing all this type of analysis using purely production data. So we have published few papers like data analysis of the Permian Basin, the data analysis in Eagle Ford, and we are trying to apply the reverse engineering types of thing also. Like if you have production data, can you predict or can you get a conceptual model of a reservoir inside what is going on, and conceptual model of the movement of oil and gas from deeper to upper or upper to deeper, normally deeper to upper. We are trying to understand that also, fluid movement using the production data. So this is the summary of mainly for data analytics part. And you can see that we can apply machine learning for geoscience areas and other areas also. And there are many machine learning, improved machine learning algorithm available right now. Mostly they are open source data. And we have to develop some integrated model with geoscience and engineering. Sometimes they work separately. I know many geologists, they work separately without reservoir engineers. So we need some integration between these two, and we'll have synergetic effect. And machine learning helps for better characterization, some real-time decision making and optimization also. It improves the recovery factor. And data analytics can discover non-intuitive relationship which we cannot discover using traditional methods. Finally, it can reduce your investment cost, drilling cost, or fracturing job cost. It can reduce the risk of seismic activities. It can reduce of environmental impacts like methane emission. And thank you for your attention. I am happy to answer any question.
Thank you, Palash, for the great talk. So if any of you have questions, please feel free to unmute yourself and ask.
Thank you so much, Palash. Appreciate you giving the talk with us. It's good to hear your progress and your very interesting research questions. I had a broad question about all these kinds of tools as they apply to areas like geothermal, for instance. Mm-hmm. What is your personal view of the role of data and analytics, but maybe coupled with physical modeling? When it comes to geothermal in particular, the issues are probably not exactly the same as those in oil production. And so in particular, there's prospection, there's hazards, there are different questions. What is your overall broad view of the role of data analytics for, let's say, geothermal in particular?
I think we can apply, of course, geothermal is little different, but its subsurface flow is exactly same like oil and gas. You are flowing the water instead of oil in geothermal. So we can apply the similar technology for temperature mapping, mainly stress mapping. I would say because thermal stress is an important factor in geothermal, where we are injecting cold water and we are trying to produce hot water, and there is a lot of stress changes. And if we can apply machine learning for stress mapping, that's most important. Then over temperature. Temperature is the second important thing. We can map temperature distribution over the time using machine learning. And third, I think, is the mineralogy. So we are injecting hot water, cold water, and producing hot water. There is a lot of mineralogical change. Sometimes at the hot condition, some mineral will dissolve in the water and it will deposit in the pipeline. It sometimes deposit in the boiler or the steam separator. Sometimes when we are flowing from one well to another well, it clogs the porosity. So third is the mineralogy. I think we can apply machine learning for three things: stress, temperature profile, and mineralogy. So if we can develop some machine learning application to identify these three things, it will help geothermal industry overall.
Thank you.
Yeah, I worked with Joe and John for EGS, Enhanced Geothermal System.
Right.
But it's mainly modeling, not traditional modeling using commercial simulator, numerical simulator.
Oh, I see. Reservoir simulators?
Yeah, reservoir simulators. And we have developed some surrogate model using ANN and some polynomial equation. We have some published paper, but we haven't applied machine learning like to map temperature, stress, or mineralogy.
Thanks for your talk. Can you say more about the details of how you would use machine learning to estimate the state of stress in the subsurface?
Yeah, I'm not stress specialist. Yeah, I'm not sure how to do that, but I think we can apply this type of convolutional type LSTM model. So that convolutional model is mainly coupling two things: spatial relationship. Convolutional is mainly for finding the features in the photos or images, and LSTM part is the time series model. So the coupling these two, that convolutional LSTM, we can apply how stress will change with over time. And I don't know how do you get signal from stress, because I am a chemical engineer specialized in oil and gas, and I'm not mechanical engineer or stress specialist. So I think I cannot answer your question properly.
Okay, thanks.
So Palash, did you have a chance to check the influence of the look back data on your LSTM model for the precision accuracy? How?
Yeah, so let me show you this model first. If you see that this completion is very complex, like five sort pattern, and we have some corner oils, we have some intermediate oils, so we have like three kinds of oils. Corner oil has two surrounding injectors. In the middle, we have like three. Middle means on the side edge, we have like three surrounding injection oil, and the middle we have like four surrounding the injection oils. That's in the middle, it's a pure 5-spot, but in the side, edge, and corner, they are not. And this reservoir is really, really complex. It's complex in porosity, complex in permeability. And that's why, although we have chosen like, okay, the production is influenced by only the surrounding oils, surrounding injection oils, sometimes it's not true, because there may be some high porosity channel connecting between two oils that are located far from each other. They are maybe connected to high porosity, high permeability zone. So we need some other systematic ways to find out the connectivity among the oils. Then we can choose the correct input. But based on our like conventional knowledge, that the best input would be like surrounding injection oils for the production from producers. But actual details analysis must be done to find out the connectivity.
Let's see.
A quick question.
Applied, yeah, it could be applied for homogeneous, but it's difficult for heterogeneous. Yeah, go ahead. Sorry.
I'm sorry. Was the SACROC data actual field data, or was it numerical data?
It's the numerical data, but models is actually very complex model. Yeah. So it's a part of phase 1 in SMART project. We have completed that, and we are going to start the phase 2 from 1st April, and we'll use the field data.
Could you say something about your concerns going from numerical data to field data? I was worried that the numerical data, maybe if there's physics that's missing, it makes things look a little better than it might otherwise in terms of making predictions.
Yes, of course, it will be more complex. And we tried to implement few field operation, like if you see the second last points, randomly shut in of producers to mimic field operation. That is one. Another thing is that this is the coarse grid model. We have fine grid model, but we had like millions of grids, and because we are working with other universities also, and we are using the same data, we are using different models. We use only grid, coarse grid model. Yes, if we use the field data, we had hundreds of wells. And sometimes I think they are not 5-spot injection scheme. They are more complex than 5-spot. And it will be totally different.
So there's a lot more data than when you go to the field data, I guess,
But
that you have to use. Or would you just use a few wells? And I guess you could still just use a few wells with machine learning. I guess it wouldn't matter, or it wouldn't care whether it would work well. I don't know.
Normally the data, you said a lot of data. I don't agree. Probably a lot of data in terms of lot of oils, but frequency of data is not good. Normally the oil company, you know, they collect monthly data, not even like day. And of course we cannot get seconds or minutes. They report data monthly, because like Texas Railroad Commission, they have a rule for monthly data. I think they don't have rule for daily data reporting. So yeah,
so
frequency is like, yeah, go ahead.
So the operator isn't having to release any more data, because I mean, this is a big research site for CO2 projects, but the operator isn't providing any more data than they provide to the Texas Railroad Commission.
Yes, I think they will provide only monthly data. Monthly.
Okay. Yeah. Okay, thank you.
Are there any other questions for Palash? Well, if not, now let's thank Palash again for the great talk. And there will be lunch provided in the second floor. And since next week is spring break, so we will see you in 2 weeks for our next WISH seminar. Thank you all for attending, and thank you, Palash, for giving this great talk again. Thank you.
Yeah, thank you for the opportunity. Yeah, thank you.